Hello friends, in this video, we will be deriving the Jacobian of multivariable calculus. This is a result often used when solving integrals involving more than one variable. The proofs of this result, most commonly found on YouTube and elsewhere online, typically deal with the simpler cases of 2 or at most 3 variables. For these cases, geometric pictures are often used, which involve integrating within an area on a plane for the 2-variable case, or within a 3-dimensional volume for the 3-variable case. While such pictures are quite intuitive for these cases, they are quite difficult to generalize to cases involving more than 3 variables. Furthermore, as we shall see, such a geometric approach is entirely unnecessary and may be completely missing the point, which is all about the equivalent ways we could solve the same integral using alternative sets of independent variables. The key point is independent variables. So the Jacobian formula is in fact very general and could be used before we even talk about any geometry. We will now prove the Jacobian formula for the general case of n variables. But before that, let's remind ourselves what the Jacobian formula looks like. On the left-hand side is the original integral in terms of the variables z's. There are n of them. We shall use the convenient vector notation for the whole set. On the right-hand side is an equivalent integral by an alternative set of variables, x. Both sets of variables are related to each other by the functions below. This is a one-to-one change of variables, which is invertible. You can see this as the relation between the different coordinates assigned to the same point in 2 different coordinate systems. This term on the right is the Jacobian determinant, which is defined in the red box. Here we are using the Einstein's convention, where repeated indices are summed over. You can see this for the indices i's. And we are using the Leibniz formula for determinant. The epsilon symbol is the Levi-Civita symbol, which is totally anti-symmetric in its indices, with a value of 1 when the indices are in running order from 1 to n. The matrix involved is defined by the partial derivatives of z's with respect to the x's. Since the relation between z and x is invertible, this means our determinant is also non-zero. So in such cases, the Jacobian formula is applicable. Now let's explain why it is necessary to take the absolute value of the determinant. This is purely due to the convention we use for the integrals. Let's examine the integration limits on the right-hand side in details. The convention is to assume that the upper limit of an integral is always larger than the lower limit. We indicate an upper limit by a plus superscript and a lower limit by a minus. An example from the single variable case should clarify our point. In this integral, we are following our convention. The upper limit z2 is larger than the lower limit z1. Let's change variable to x. For one variable, this is straightforward. dz is simply equal to dx times the derivative of z with respect to x. If this derivative is positive, z would increase with x, and the integration limits in both integrals would already satisfy our limits convention. dz dx could also be replaced by its absolute value due to its positivity. This is just a one-variable Jacobian, and we have the standard result. On the other hand, if this derivative is negative, that is, z and x increases in opposite directions, this implies that x of z1 is greater than x of z2, which is the opposite of the relation between z1 and z2 and is against our convention. We can fix this by pulling out a minus sign, then adding an absolute value to dz dx. This minus sign could then be used in switching the limits of the integral. In this way, the new upper limit will be larger than the lower limit, following our convention. Thus, the absolute value is the simple consequence of the integrals on both sides satisfying the same limits convention. This is the standard result. Of course, there is nothing to stop us from integrating from a larger number to a smaller number. In this case, we would then have this equation. The point is that by adding the absolute value, both sides will follow the same convention. Note that even though we have established this result for one variable, the absolute value will automatically carry over to n variables, because we are going to construct our proof by the process of induction, in which what is true for lower n will also be true for higher n. We shall see this in a moment. Now let's prove the Jacobian formula for n variables. Here's our strategy. First, we shall prove this for two variables in two special cases. These can be done easily from what we know about changing variables for the single variable case. Using these two special cases, we can prove the general result for two variables. This exercise with two variables will then show us a way to prove the n variable case. Basically, we shall proceed with the method of induction. We will show that if the Jacobian formula holds for n-1 variables, then it must also hold for n variables. With the results for the smallest n already in the bag, this will complete our proof. As a start, we shall first prove an important identity about the Jacobian determinant, which is key to the proof. Let's show that the Jacobian satisfies the chain rule, just like an ordinary derivative. The Jacobian between z and x is equal to the product of the Jacobian between y and x, and that between z and y. Recall that the Jacobian between z and x is just the absolute value of the determinant of this matrix. By the chain rule of partial derivatives, partial z partial x is just equal to the multiplication of partial z partial y with partial y partial x. We can see the right-hand side as the multiplication of two matrices. Remember that we are using the Einstein convention, so the repeated index k is summed over. Taking the determinant, and remembering that the determinant of the product of two matrices is just equal to the product of their determinants. We have our result. Thus, the chain rule of the Jacobian is the direct consequence of the chain rule of partial derivatives. This simple result shall be a cornerstone to our proof. Let's start with the proof for two variables, where the Jacobian is the following determinant. This should work for a general invertible map between y and x. Let's prove this by first looking at two special cases. For the first case, y1 is just equal to x1. This component is not changed at all, while y2 is some arbitrary invertible function of x1 and x2. For the second case, it's the other way round. y2 is unchanged, while y1 is dependent on x1 and x2. The Jacobian formula can be proved easily for these two cases by just applying the single variable result, as we shall see. Let's change variables for our integral according to the first map. x1 under the integral of y2 can be treated as a constant, since we are going to integrate over x1 only after y2. This means f can be treated as a single variable function of x2 under the integral over y2. Now all we have to do is to change the variable of this integral to x2. This can be simply done with the Jacobian formula for the single variable, which is just a straightforward application of differential calculus, telling us how y2 varies with x2. Remember that x1 is to be treated as a constant at this stage. Pay close attention to this absolute value. We have justified this from the integral convention for the single variable case. See how this is carried over to the two variable case. We claim that the integral on the right-hand side can be written in the form of the standard Jacobian formula, and that this derivative is actually the Jacobian, which corresponds to the map above. This is easily seen by calculating the determinant directly. According to the map above, the first derivative is just the delta symbol, which fixes the value of I1 to 1. Since the epsilon symbol is antisymmetric with respect to its indices, the only possible value of I2, where epsilon is non-zero, is 2. And the epsilon for this case is just 1. Thus we have shown that this derivative is actually equal to the Jacobian of the map above. Therefore, the Jacobian formula for the first special case is proven. Let's move on to the second special case. This ought to be straightforward, since we can get this from the first case by switching the variable label 1 and 2. For the non-trivial part of the map, switching 1 and 2 within this argument doesn't really change the result, since we are dealing with an arbitrary function after all. So by this argument, we could be certain that the Jacobian formula will hold for this second case as well. But to familiarize ourselves to this argument, let's quickly work through this case anyway. Thus, we have shown that the Jacobian formula holds for the two special cases above. Let's now combine these results and prove this for the general case for two variables. Our goal is to construct a composite map out of these two, such that each variable is transformed in a non-trivial way by arbitrary invertible functions phi1 and phi2. Let's cast map2 into a more generic form. The map capital phi1 maps the input variables S into an output following the pattern above. This is how we try to insert the function phi1. The second component is unchanged for this map. Note that S is just a placeholder for input variables. For the first map, let's cast this into the generic form capital phi2. The first component is unchanged for this case, but for the second component, we introduce phi2. But we need another function within phi2. Since we wish to implement our goal by making a composite map out of these two, like so, the function within phi2 should be this, so that we get phi2 of S. The inverse map is to reverse the effects of capital phi1 on the first component of S, which is the only component it transforms, while S1 here will just be phi1 of S after composition. Thus, our composite map below really results in a general two-variable transformation, and our goal is reached. But because the map capital phi1 belongs to the second type of transformations, and capital phi2 belongs to the first type, and the Jacobian formula holds for both of these types of transformations, using the chain rule on the Jacobian of their composition would immediately prove that the Jacobian formula holds for the general case of two-variable transformations, which is what we have set out to prove. Now let's go through these steps in details. First, let's give these two maps a more convenient notation. Write z as a function of y, and y as a function of x, and the composite map below just becomes the above. This is a general invertible transformation between x and z. Remember that, as we have shown earlier, both the transformations z of y and y of x satisfy the Jacobian formula. Starting with the integral in the z variables, let's transform to y using the Jacobian formula. Then from y to x. And using the chain rule of the Jacobian, these two can be combined into the Jacobian between z and x. Therefore, the Jacobian formula holds for a general two-variable transformation. Now, let's prove this for n variables. In this proof, we shall assume that the Jacobian formula holds for n-1 variables, then show that this would imply it also works for n variables. This would complete our proof by induction. Let's start with an integral of n variables. For this case, we can have its own version of the maps capital phi1 and phi2. As before, S is the placeholder input variable. What we need is the composition of these two maps to give a resulting mapping between z and x in terms of n arbitrary functions, which is what we did for the two-variable case. You can see that this is true from the definitions of these two maps. First plug x into capital Phi 1. Then plug the result into capital Phi 2. The first component is unchanged, and we just get the function Phi 1. As for the rest, due to the inverse capital Phi 1, we also get the rest of the n-1 functions. What the inverse function does, as we can see above, is to reverse the transformation of x to give us back x, which is then plugged into Phi 2 to Phi n. Thus we see that the composition of these two maps really gives us the desired relation between z and x. But please bear in mind that we have not yet shown that these two maps for n variables satisfy the Jacobian formula like we did for two variables. We shall deal with this in a moment. Let's switch to a more convenient notation. Capital Phi 2 is the map between z and y, and capital Phi 1 between y and x. Let's also replace these complicated-looking nested functions with just zi of y, where I runs from 2 to n. That is, all the components except 1. This component is unchanged. Let's go back to our integral. We shall single out the integral involving z1. Under the integrals of z2 to zn, z1 can be treated as a constant. z1 is also not transformed by our map, and is just y1. We can effectively treat these as an integration of n-1 variables. Since we have assumed that the Jacobian formula holds for n-1 variables, let's apply it here. Transform this into an integral in terms of the variables y2 to n, according to the map above, where the Jacobian determinant is given by. Note that all these indices does not include 1, including those we have summed over. Since we are treating y1 as a constant, as its turn to be integrated has not yet arrived. The epsilon symbol is still totally anti-symmetric and is equal to 1 if its indices are in running order from 2 to n. Since the first component is not changed, we have so we can insert this derivative back into the integral. This is also equal to its absolute value. Now we will show that this product is actually the Jacobian determinant for the map above. Let's forget about the absolute value for now. We can insert it at the end. This epsilon symbol with n-1 indices can be replaced by 1 with n indices, with the first index fixed to 1. Remember that none of the indices above are 1. This n-index epsilon is totally anti-symmetric and has the value of 1 when the indices are in running order from 1 to n. Once we replace the epsilon above with the 1 below, we can then extend the sum of the indices to include 1. Since the epsilon below will be 0 anyway, if more than one of its indices are equal. Furthermore, since partial z partial y is only non-zero for the first component of y, we can replace this pair of index 1 with the full sum. Thus we find that this product is really the n-variable Jacobian, which corresponds to the map above. Now, let's make the transformation from y to x according to the second map below. This time, it's the components 2 to n that are unchanged, while the first component is transformed by the arbitrary function phi1. It's probably more intuitive to notate this as y1 of x. The integrals y2 to yn would then be unchanged. Let's move them outside and move the integral y1 inside. Under the integral over y1, the variables x2 to xn could then be treated as constants. Note that all these y's are functions of x by the map below. But only x1 is considered a variable under the integral over y1. So we could treat y1 as a single variable function of x1. All these are in a way obvious, since we are after all integrating over a single variable. Thus dy1 is related to dx1 by just the following. Here, we have inserted the absolute value according to the integral convention for single variable. We will now show that this derivative is in fact the Jacobian of the map between y and x. First notice that this delta symbol fixes the index I1 to the value 1, and that this delta is actually equal to the following epsilon symbol. It is not difficult to see that this epsilon is equal to the following. The indices 2 to n are now replaced by ones that are summed over. But that's okay, since these derivatives are all delta symbols which fixed these indices to their original values. This is according to the map below. Now we can use this delta symbol to pick out the derivative partial y1 partial x1 out of a sum. But this is the Jacobian we are looking for. And by the chain rule of the Jacobian, we have. This is just the Jacobian between z and x. Let's make our changes of variables explicit within the argument of the function f. These arguments are precisely the arbitrary functions phi1 to phi n. Again, we can replace these by a more intuitive notation. Thus, we have shown that the Jacobian formula holds for n variables if it were true for n-1 variables, This completes our proof by induction. This is a very general result, and is applicable even before we talk about any space, time, or geometry. These variables can be quite arbitrary. What this result says is that as long as the integral on the left-hand side is well defined, we can evaluate it using any alternative variables which are related to the original ones by a one-to-one invertible map. If you like this video, consider giving it a like and subscribe to this channel. And remember to press the notification bell so that you'll know when a new video is ready. See you next time, and thanks for watching.